Welcome to the first episode of Proof, where I'll be proving why certain things like the natural log of x become 1 over x when you derive them, and how sine x becomes cos x, and whatnot. But first, because a lot of that you use things like limits, or you use the long way of derivatives to solve, I will be showing you the long way to solve, which is limits. I've said this before, but a derivative is when you're finding the slope or the rate of change, and when you do these little tricks and whatnot, they're to do the derivatives, which are not tricks, but just the way you do derivatives. It's actually the fast way. Here is the slow way, and I'll show you how to do them. This is just your function. I haven't labeled anything, but you just have your function, and when you derive your function, you get the limit as h approaches 0, f x plus h, which is your function after you input h. You minus it by your original function, and then you have it all over h. This probably won't make sense unless you've seen it before, but I'll do some examples. H is the change in x. I only write h because if you have x plus the change in x, I think it's, have 1x and have something else. So I've labeled change in x as h because you want h approaching 0, because you want it to be, you've got 2 points and you want it to be as close together as possible. You want the change, you want to know the slope or the rate of change on a graph, or whatever you're doing this for. But generally speaking, on a graph, you want to find the rate of change. You don't want the change in x to be varied or different or too far apart. You want it to not be 0, because you can't do it if it's 0. You want it to be almost touching. You want the 2 points to almost be touching, but not quite. And that's why it's as it limits as it approaches 0, because you don't want it to be 0. H can't equal 0. Otherwise, it screws the whole thing up, because if you're dividing by 0, well, it's 0. So that sort of puts an end to it fast. So I'll show you how to do it. You get your function ready, you simplify it down as good as you can, as simplified as possible, and then you start taking away the h's. And anyway, I'll show you exactly what I mean. So let's start with an example. We have let's say we have a function x squared. The derivative, the long way, limit h approaches 0, f x plus h minus fx all over h. You have to write this all the time. All the teachers that I've spoken to and have marked my work, they said if you don't write this, you actually get marks taken off. Like, I'm only writing it to show you, but if you're doing this by yourself at home, I don't know why you would do it the long way, but if you are doing it by yourself, or it's not going towards anything, don't have to write it, but it's always, good form to follow notation. Anyway, that's a must. But here's the bit where it becomes a bit different. And I'll do it first, and then I'll show you exactly what I did. So here you have fx, which is f prime of x. This function has invisible brackets. They're now visible because I drew them, but it has invisible brackets. And basically, with this bit here, when you have f and inside the brackets x plus h, you're basically replacing the variable inside with x plus h. Or you're replacing it so the variable is, in this case, it's x plus h. And so you would replace the variable inside with x plus h, so x squared in this new function here would become x plus h squared. and then you minus it by the original function. The original function is just x squared, so you just write x squared. This is the only different part where you replace the x with x plus h, and then you divide that all by h. Now the simplifying part. We're going to expand these brackets. So if we write limit again, h approaches 0, expand them out, x, we would have x plus h brackets, and then we'd have another set of brackets and x plus h. I'm not going to take the time expanding them, I'm just going to do them on the page. So you would have x multiplied by x squared, plus x, then you would multiply that by the h, and then over here you would have h and multiply it by the x, so we'd have 2xh, then you'd plus that to h times h squared, minus x squared all over h. We can do some eliminating. We've got an x squared here and an x squared here, and because that's a positive and that's a minus, cancel them out, no problem. We can also cancel out the h on the bottom because we have 2xh plus h squared. We can get rid of 1 here, and we can get rid of 1 here, and get rid of 1 on the bottom. So what we're left with, limits as h approaches 0, is 2x plus h. Now, essentially what it's saying is, if you type this into your calculator, 2x plus 0.00000000001, it would round up, or it would round down to 2. No, you can't have 2x, you can't put that into a calculator, that's a bad way of saying it. But if you added a very, very, very small number, the one like I said before, you would just end up with 2x, because why would you write 2x or 2x plus 0.00001? It's essentially you're adding something on, but it's so small and so insignificant that you don't even bother. It's a little bit confusing to wrap your head around for some people. But essentially, the limit as h approaches 0 is 2x. Because h is so small, you don't even worry about it. It doesn't affect the equation at all. And if you were to do this, like normal derivatives, where you had x squared, you would just do the power rule. Bring the power down and take 1 off the top. So you'd have 2x to the power of 1. We have 2x to the power of 1 here. This is just the long way that no one likes doing. But because when I'm doing proof and showing you how you get certain things, you sort of need this. But anyway, I'll do another example. Let's say we have, I'll make this one a bit longer. We have example 2. We have our function. It equals x squared plus 3 over 4. Same as before. The derivative, limit as h approaches 0, fx plus h minus fx all over h. This is our variable x here. So when we are doing the adding h part, just write the limit h approaches 0. When we're adding the h, we add it into this bit, not all of it, just this bit. So we end up with x plus h squared plus 3 over 4. We're just adding h to the variable, which is, we're just adding the change in x, because you have your point x, and then you have your change in x, which is all over, wherever on the curve. But if you make it so small, it's almost like they're touching, and that's what we're getting to. You're approaching the limit. As h approaches 0, the change in x approaches 0. But anyway, so we subtract that by the original function, which is just x squared plus 3 on 4, all over h. Okay, now that we've written it out, we can simplify it. Because I'm gonna do something on the bottom first, and then I'll focus on the top. But because we have a h on the very bottom, we've got this bit up here divided by this, then divided by this again. Think about, you know how, think about it this way, h over 1. Whenever you've got 4 over 1, it's just 4. H is the exact same as h over 1 because that's I can't really think of the explanation right now, the definition, but if you had a 4, that would equal 4 over 1. So if you had h, that's the same as saying h over 1. When you divide by a fraction, it flips it and brings it right side up. That means that we'd have a limit as h approaches 0, and we'd have 1 over h multiplied by x plus h squared plus 3 all on 4 minus x squared plus 3 on 4. Therefore, we rewrite the limit as h approaches 0. We would just multiply h onto the bottom of each fraction, onto the 4's. And we'd end up with it all joined in 4h. Because these have both got the same denominator, you can actually join it already, but I'm going to do it in one step now. And because if I multiply h onto that and h onto that, they'll both have the same denominator, so I can put this minus up here and join it together. We'll expand these brackets out, just like before. We have x squared plus 2xh plus h squared plus 3. And then, now, here's where the minus of this bit comes in. Because it's minus that, we would multiply the minus to the x squared and to the 3. So we have minus x squared, and we'd also have minus 3. Because we're subtracting this from that. So if we do some eliminating, we've got an x squared minus x squared. We've got a 3 minus a 3. And what we're left with is 2xh plus h squared, all on 4h. We can get rid of a squared and get rid of a h and get rid of a h on the bottom. So we get rid of one h from each bit. Rewriting this, we get, as h approaches 0, 2x plus h on 4. Okay, now we're going to split this. I'll just write the derivative here. Should have wrote them for all of them, but doesn't matter. Now we're going to split it again, or undo the joining. And we're going to have 2x on 4 plus h on 4. We can, because it's 2 over 4, that's the exact same as 1 over 2. So, in the simplifying stage, we are going to simplify it. The derivative, limit, as h approaches 0, is x on 2 plus h on 4. We've just simplified this because 2 on 4 is the exact same as 1 over 2, x on 2. Okay, now that we've got this, we do the h approaches 0 part. When you have a number that's almost 0, think of it as 0. It's not supposed to be, but think of it as 0. If you had 0 over 4, that would be 0. So if you had a number that was almost 0, so close to 0 on 4, you would end up with a number that would end up being so close to 0. Therefore, we can just cancel it out and have limit of h approaches 0, x on 2. And if you go back all the way through this long process where we started, and we have x on 2 plus 3, if you derive that, you would end up with x over 2. This is a long process. Not many people do it at all unless they're told to. But that is just showing you how to do it, so when I do my future videos you can understand. Thanks for watching. I hope this helped.